2sum is a very classic problem. Given two integer arrays and some target integer, we want to find one value from each of the arrays such that the sum is equal to the target integer. And it would be nice if we could also find the indices of these values. Of course, it is possible that no such pair of values exists, in which case we want to return some value indicating that. Here's some basic code outlining a test. So this will run a function solving this problem that we have not implemented yet. We'll give it these arrays A and B. So our target value is 12 in this case. This can be done with the value 4 from array B and the value 8 from array A. This is the unique solution for this input. So we would expect to see an output of 1 and 3. Let's look at a very quick implementation of our solution for this problem. The first thing that we could do is look through all the values in A and look through all the values in B and check if they sum to K. This would give us a very quick and easy solution to implement. So first we have to iterate through all the values in A. And then we have to iterate through all the values in B. And then we simply have to check if the two values sum up to K. If so, we return this pair of indices. If we never find such a pair, then we just want to return our value indicating that no such values in the arrays exist, which we chose as -1, -1. We can quickly run this code to test that it outputs our expected value of 1, 3. And it does. So the time complexity of this solution is actually quadratic, since we're iterating through all the values in A, and for each of those values, we're iterating through all the values in B. And assuming they're about the same size, that will give us a very quadratic runtime. So this is quite slow, and we can actually do much better. This style of embedded for loops followed by an if statement often leads to a very nice data structure-y solution, and that's exactly what happens here as well. So we're going to replace this if statement with an equality sign with an if statement that uses a hash map lookup. So the first thing we have to do is create our hash map, and this hash map is also going to help us eliminate this second loop here. So the hash map is going to be a hash map that contains indices and values from the array B. And we're just going to put them all in the array. So we're going to set B map of bi to be equal to I, because we're actually going to be looking our values up, and then the auxiliary information that we will want when we return is just the index. We're not going to be using the index to determine if there is an answer. Let's eliminate the second loop, and let's change our if statement around a little bit. So first off, notice that we can use a little bit of algebra to move this AI over to the other side. And then we just want to check if there is some bj that satisfies this equality. And that's equivalent to saying we have such a bj, in other words, B map contains such a value. And if so, then we can return the index corresponding to that value. And we can run this once again to get the same output. So here we have another version of twosome. This time we only have one array, and this actually makes the problem a little bit trickier. So even though we've reduced the number of arrays, we now have to worry about an extra case, and we'll talk about that in just a second. But aside from that, everything is the same in this problem. Here we have yet another test case. In this case, we're looking for a value of 16, and the way we get that is from adding up this 4 and this 12. And keep in mind, the indices, or the values in the array, have to be distinct from each other. If you have two of the same value entered into the array twice, that's okay. However, you cannot use this 8 value twice. Let's try our naive solution first again, our quadratic naive solution. This is the very simple solution that we can do, and it is, again, very simple in this case too. So we're just looking for distinct pairs, so the nice way to do that is to iterate through all the values in A using an index, and then iterate through all the values in A larger than our last index. And then if we find a valid pair, we can again return true, or return our pair. We have found a sum in that case. So if AI and AJ, in this case, add up to K, then we return I and J. And once again, if we never find such a pair, then we should return -1, -1. And we see 2 and 3, which corresponds to our 4 and 12 from before. So if we want to find our faster solution from before, we have to make a bit of a modification to what we did before. So last time we had a hash map containing the array B, but we don't have an array we can just completely eliminate right now. But let's store everything in a hash map for now anyways. So let's use the same hash map as before. So once again, iterate through all the indices of A and insert the same as before. We key by the values in A, and then we add the indices as auxiliary information. And now we can attempt to do what we did before, where we replaced the second loop and also this if statement with our lookup. And let's run this. And we get an output of 1, 1, which is invalid because these aren't distinct indices. But if we go and look at what 1 is, it is that 8 value from before. So the problem now is that we are using the same value more than once. And there's actually another small problem. It doesn't really affect our solution directly, but it will lead us to a nice fix for what we're doing right now. And that is that we could end up with the values 4 and 12, or the values 12 and 4. We're actually not making a distinction between the two orders. So one way we could solve this is by only having the indices from before the current index stored in our map at any given time. And this is actually quite simple to do. Instead of looking through A twice at different times, we can actually do this map update inside our existing loop. And this way, a map will only ever contain entries from before the current index. And in fact, if multiple of the same number exist in A, it will actually give us the most recent one. So we would actually expect to see an output of 3, 2 now instead of 2, 3, because we're going through the map forwards, and the second value is always going to be smaller since it comes from before our current value, everything we've seen already. So if we run this, hopefully it will not give us the same 1, 1 answer as before. And it does not. It gives us exactly what we expected. And the runtime of this is, of course, just like the improved version of the last problem, O of n.